This topic for AP Chem is elemental composition of pure substances. And in this topic, we have to find the chemical formula of a substance from given information. Now, a pure substance is what we're going to talk about in this section, and that is an element or a compound, something that has a specific chemical formula, whether it is a diatomic element like oxygen, so it's O2, or a covalent compound like water, so it's H2O, or even an ionic compound like salt, so it's NaCl. You should have in your high school level chemistry talked about percent composition. And in percent composition, we have a little basic calculation down here where we take the mass of the element over the total mass of the compound times 100. We keep doing that over and over and over for each element. And once we do that, we add up the total percents, and you should end up with percent composition close to 100%. It may be a little over or under depending on significant figures. So if you haven't already started reviewing polyatomic ions, you probably need to. You need to have a basic level of memorization of polyatomic ions because AP is going to need you to know what their charges are sometimes, and it makes it easier if you just know the ion's charge to be able to figure out the chemical formula or to be able to figure out the charge of the other ion that is attached to the polyatomic ion. So before we can even do this problem, we don't have a chemical formula. It says, what is the percent comp of each element in the compound ammonium phosphate? Well, ammonium and phosphate are both polyatomic ions. You're not going to find either of them on the periodic table. They need to go into your brain. And so ammonium is NH4 with a positive 1 charge. And then phosphate is PO4 with a negative 3 charge. When you're doing an ionic compound, my positive and negatives have to cancel. So in order to get to a neutral 0, I need positive 3, which means I need 3 ammoniums. So when we do that, I need to use a set of parentheses. The 3 goes on the outside. And then I only need 1 phosphate because its charge was already negative 3. So now I would have 3 times a negative 1 or positive 1 for each of these, which would give me positive 3. That would cancel my negative 3. So then it asks for me to find the percent composition of each element within the compound. So when you do this, you're going to separate out all those elements. So I have 4 elements in this compound. I have N, I have H, P, and O. So what I do is I typically get everything set up because I'm going to create a ratio with each of these. And then I fill in my top information, and I come back in and fill in my bottom information. So for nitrogen, because of this subscript that is on the outside of the parentheses, I have to distribute that in. So right now there's an understood 1 nitrogen in the parentheses. I'm going to multiply it by 3. So 3 times 1 gives me 3 nitrogens. So the number I'm going to write up here on the top is going to be the mass of nitrogen times 3. So let me grab my calculator and my periodic table. So I'm going to do the mass of nitrogen, which is 14.01, times 3. And that gives me 42.03. So that's what I'm going to write on the top of my ratio right here. The unit is grams. Then I have hydrogen. So for hydrogen, again, I've got to look at this subscript on the outside and the subscript on the inside of the parentheses, distribute it in by multiplying. So 3 times 4 gives me 12 total hydrogen. So the mass I'm going to write over here is 12 times the mass of hydrogen, which is 1.008. And that gives me 12.096. Then I'm going to look over here for phosphorus. There's only one phosphorus because there's no subscript, so it's an understood 1. So if I look on my periodic table, the mass of phosphorus is 30.97. And then oxygen, I have 4 oxygens because of the subscript. So again, I'm going to do 4 times 16, and that gives me 64. It's technically 0.00 because it's actually 16.00 times 4. So then I'm going to add these top numbers, and that gives me my bottom number. So I have 42.03 plus 12.096 plus 30.97 plus 64. And that gives me 149.096. And I didn't leave myself a lot of room to put this on the bottom of the ratio. Then I'm going to calculate these out and around based on sig figs. Actually, not sig figs, so we're going to round it to the hundredths place for each of these. So sig figs are used for whenever we have a measurement. Neither of these things are really measurements. They're things that we get from the periodic table. They're considered a constant. So percents are usually rounded to the hundredths place. So for my first percent, I get 28.19%. The unit of grams cancels whenever I divide. In the second one, I get 8.11%. The third one, I get 20.77%. And the last one, I get 42.92%. Actually, 93%, because the 5 that I'm dropping off is going to make the 2 round up. So then I want to add these together to make sure that my total percent is correct. And I end up with exactly 100%. Again, it'd be okay if it was a little above or below, as long as it's close to 100%. So what this means is out of the total mass of this total compound, that the nitrogen offers about 28% of the mass, hydrogen 8, phosphorus 20%, and then your oxygen about 43%. So it makes up the biggest percentage of mass in this compound. Unfortunately, AP is not usually going to ask us a question like this. You should have done this in your regular high school level chemistry, and it's pretty easy, but unfortunately, AP doesn't ask us that. Now, in this one, it says 2 different ionic compounds contain only copper and chlorine. Both compounds are powders, one white and one brown. An elemental analysis is performed on each powder. Which of the following questions about the compounds is most likely to be answered by the results of the analysis? And if I look at these options, sometimes you have to think about the informations that it gives you, and sometimes we have to cancel out things that are not as logical. So in this problem, we have what is the density, what's the formula unit, what is the chemical reactivity, or which of the 2 compounds is more soluble in water. At this level in chemistry, we don't have the knowledge yet to answer a couple of these, so I'm just going to go over very briefly a couple of the topics. Let's start with solubility. So we will learn later on there's a pretty basic way to memorize solubility. And with solubility, we memorize the concept of SNAP. And with this, AP's typically only going to ask you about these 4 things. So sodium nitrate, ammonium, and potassium are always soluble. And then there are some other things that end up always being pretty much the same solubility. So in this one, I have copper and chlorine. So it doesn't really matter what the combination is of these things, how many coppers and how many chlorines. They're the same 2 elements. So they're going to have the same solubility. So they're not going to ask you that because it's not specific to this concept. Ask what's the chemical reactivity. Again, if I go back up here, I have copper and chlorine. So those 2 elements are the same elements, so they're going to have the same chemical reactivity no matter what the ratio is. Density. So density is a really great way to figure out the composition of a compound or an element because every pure substance has a specific density. The problem is the fact that they told us these were powders. So if I have a powder, if I'm trying to measure the density using the fact that it's grams per some unit of measurement cubed, some volume, you can't really use any calculations to measure the volume of a powder because it's going to take up a different amount of space because it is a loose substance. The other option we have is finding density using water displacement. Well, that's going to be a problem too because some of this is going to dissolve whenever you put it into the water, so that's not going to give you a true density. So because of that, if it was a solid substance, I would say density would be reasonable, but it's not. If it's a solid, like metal substance, powders are solid, but if it's a solid metal. So my option is, what is the formula unit for each of the compounds? Some of our multiple choice questions you have to think a whole lot on, and some of them the first answer is obvious. So this is probably a new topic to you. We don't often get time to cover this in our high school level chemistry. So there are a few words that are going to be new. We're going to have empirical formula and molecular formula. Your empirical formula is going to be the simplest number of your ratio in a simplified form. This is what we're going to see whenever we see ionic compounds. They always have their empirical formula because when we're doing the chemical formulas, we always figure out the smallest number of each thing that can be equal to 0 to cancel out the charges. Molecular is the other option, and it's the actual number of each element in a compound. This is going to be more likely to be used for covalent compounds because in covalent compounds they are sharing electrons and they can bond in a lot of different ways. Nitrogen and oxygen bond as NO, NO2, N2O, NO3, N3O. There's all kinds of options. And so because of that, you typically see the molecular formula, which means it has not been reduced to its simplest form. So just to get the understanding, this next thing says, what are the empirical formulas of H2O2, Na2SO4, and C2H4O2? So you're going to simplify the ratios. So H2O2 can be simplified by 2. So all that's going to be left is hydrogen and oxygen. The problem with that is we don't now know what the ratio is, and so it could be water or it could be H2O2, which is hydrogen peroxide. We don't know, and that's the reason it's important to have the molecular formula for our covalent compounds. The next one is Na2SO4. Well, it's already simplified, as all of your ionic compounds are going to be. And then I have C2H4O2. That can all be reduced by 2, so it's going to be CH2O. Again, this is the simplest formula, but there are a lot of compounds that form between C, H, and O, and we need to see those subscripts to know which one is which. To solve for the empirical formula, which is most likely what AP is going to do in a variety of different ways, you are going to be given some sort of data, and you are going to have to figure out what the chemical formula is from some sort of laboratory data that they're going to have in a data table. So my first thing is, if I am given the percents, like remember a minute ago we just figured out the percent composition. If I'm given percent composition, I can use that to figure out my empirical formula. So we're working backwards from percent composition. I'm going to take that percent and just change it to grams. When they give you the percent, it's out of 100%, and that just correlates directly to 100 grams. There's nothing weird you have to do. You just change that percent sign to a gram. Then I'm going to convert all my grams to moles using a basic gram to mole conversion. Then, once I have all of my moles, I'm going to divide each amount of moles by the smallest amount of moles, and that's going to give you a number. Sometimes that's a whole number. Those are our happy questions. Sometimes it's not. If it's not a whole number, then I use this set of rules. 0.1, 0.2, I'm going to round it down. 0.3, 0.4, I'm going to multiply by 3, and that's going to get me close enough to a whole number that I can round it again. 0.5 is going to multiply by 2. 0.6, 0.7, again, I'm going to multiply by 3. 0.8, 0.9, I'm going to round up. I do this to all the moles, even the ones that are already a whole number ratio. When you do this to one of them, you have to do it to all of them. So let's work out a couple problems. So this one says a compound was analyzed and found to contain 13.5 grams of Ca, 10.8 grams of O, and 0.675 grams of H. And then it says, what is the empirical formula of the compound? So my first thing is to convert my masses to moles. My second thing is divide all the lowest number by the lowest number of moles. And then my third one is to use the mole ratio to figure out the chemical formula. So this one's already given to me in grams. If we go back here, one of the steps said convert the mass percentage to grams, but it's already done for me. So I don't actually have to do that. I do have to go through and use those steps and solve this problem out. So I'm starting with 13.5 grams of Ca. So my first step is to convert everything to moles if I'm already in grams. If I was in percents, I would first change it to grams. So I got 13.5 grams of Ca, 10.8 grams of O, and 0.675 grams of H. Then I'm going to do a basic conversion. Where I'm doing a one-step mole calculation. On the bottom is going to be my mass from my periodic table. So for hydrogen, it's 1.008. For oxygen, it's technically the 16.00. And for calcium, it is going to be 40.08. I'm going to calculate these out. This time I am going to round to sig figs because that first number is a given in this one. So my first one comes out to 0.337. This has 3 sig figs, so this also has 3 sig figs. My second one has 3 sig figs, so again, I'm going to do the same process. So 10.8, We're doing technically times 1 divided by, but the times 1 doesn't affect it. My next one comes out to 0.675. And then my last one, I'm going to do 0.675 divided by 1.008. And it comes out to 0.670. Then I figure out which one of these is the smallest and divide by it. So 0.337 is smaller than the other two numbers. So this one's automatically 1. 0.675 divided by 0.337 gives me 2.00, which, based on my rules, I would round that to just 2. And then 0.670 divided by 0.337 gives me 1.9, which is going to round also to 2. So this one's a little bit of a tricky compound because if I write it, I can write it as CaO2H2, and AP would probably accept that. But more likely you would see this given to you in this format because OH is hydroxide, which is one of my polyatomic ions, and they would write it as CaOH in parentheses and 2 on the outside. We know that it's an ionic compound because calcium always bonds ionically, and that's something that you'll get better at recognizing as we go through the school year. AP would take either of these answers, but this is the more correct answer. So on those types of problems, they are time-consuming more than being extremely difficult. You have to go through and figure out all the different steps and practice through those to figure out that final chemical formula. This one says a compound is determined to be 43.6% phosphorus and the remainder oxygen. What is the empirical formula? So again, we're going to use our steps to work this one out. So my first thing that I'm given is I'm given the 43.6 gives me percent, where we can immediately change that to grams of phosphorus. The remainder is oxygen, which means out of 100%. So 100 minus 43.6 gives me 56.4. That's grams of O. So again, my first step is I got to convert these, change the percent to grams, then convert them to moles by doing a basic gram to mole conversion. This number is going to come from the periodic table. I accidentally wrote P instead of O. This number comes from our periodic table, so this is 16.00. And then phosphorus is 30.97. Work the problems out, round to sig figs. So I got 43.6 divided by 30.97. And I get that my number of moles is 1.41. Do the same thing. I got 56.4 divided by 16. Gives me, I need 3 sig figs again, so 3.53. This number is smaller, so I'm going to divide both of them by 1.41. This one gives me 1. And 3.53 divided by 1.41 is going to give me 2.5. So then we have the problem of these are not whole number ratios. When this happens, I have to make whatever one has a decimal into a whole number ratio. My rule was if it was 2.5, it ended in 0.5, I would multiply that value by 2. that means I also have to multiply this value by 2. So this one ends up being 2, and 2.5 times 2 gives me 5. So my final formula is P subscript 2, O subscript 5. We don't have any sort of fractions for our subscripts. So if I go all the way back here, this is where I used my steps. So on the other ones, we were getting 0.1, 0.2 once we divided through by it, or 0.8, 0.9 when we divided through by it. But this time we ended up with 0.5. So I have to multiply all my moles by 0.2 to be able to get that to the right number. And when I do that, then I end up with my whole number ratios. So this problem is giving us percents, but it's actually asking for molecular formula, which means we're going to have to do several steps. We have to figure out what the empirical formula is first, and then use this little equation where you take the molecular formula mass divided by the empirical formula mass to figure out what the number is of our ratio, and then we work that problem out. So in this problem, I have P, N, and Cl. It gives me percent, so I'm going to have to first work it out where I'm doing 26.7 grams of P, and then 12.1 grams of N, and then 61.2 grams of Cl. Again, one more basic mole conversion. We do mole conversions all the time. That is a basic language in AP chemistry. So you just need to get really comfortable with them. So then my mass for phosphorus is 30.97. My mass of nitrogen is 14.01. And my mass of chlorine is 35.45. So I'm going to do 26.7 divided by 30.97. I need 3 sig figs, so it comes out to 0.862. Now I'm going to do 12.1 divided by 14.01. That gives me 0.864. And then I'm going to do 61.2 divided by 35.45. And that comes out to 1.73. Divide through by the smallest, which is the 0.862. So this is going to automatically come out to 1. 0.864 divided by 0.862 comes out to 1.00, so it comes out to 1. And then 1.73 divided by 0.862 comes out to 1.5, 1.49, which rounds to 1.5. Same problem we had in the last slide. I'm going to have to multiply everything by 2 to get rid of the 0.5. So this ends up being 2, 2, 5. So then my formula for this one is going to be I'm sorry, something went wrong here. This should be exactly 2. I'm not sure what I did the first time in my calculator. Oh, I did times. I did times 1.73 times 0.862, which is not the right thing. So give me a 2nd to clear this out. Okay, so this ends up being 1, 1, and this down here ends up being exactly 2. Sorry for the math error. So then I have as my formula PnCl2. That is my empirical formula. That means that these are the reduced down rates. It's asking specifically for the molecular formula. If the molecular compound has a mass of 580 grams per mole. So that means that I'm going to have to figure out my mass of this compound in its empirical formula format. So now we're going to do just the molar mass of the compound. So I have 1 phosphorus, which is 30.97, plus 1 nitrogen, which is 14.01, plus 2 times 35.45, which is the mass of chlorine. And this mass comes out to 115.88. Then I use this little equation where I take the molecular formula mass divided by the empirical formula mass. So I'm going to do 580 divided by 115.88. This is my molecular formula mass because that's what they have to give you in the problem. And this is my empirical formula. Remember, molecular formula is not simplified. Empirical formula is. So then I do 580 divided by 115.88. And this comes out to 5. So then that is what I multiply into my chemical formula. So then I'm going to do 5 times PnCl2, and I end up with P5N5Cl10. And if I added the mass of that, it would come out to 580. That is the molecular formula. So on these problems, some of them are more simple than others. All of them are time consuming because you have to set up these problems and do your conversions for moles. And then you want to make sure that you are remembering to do this division step where you divide through by moles, whichever one is the smallest ratio, to be able to hopefully get smaller number mole ratios.